Last last time we had an example, no, of an ASME code wherein the material did not specify any chemical or physical properties. So we use 8,000 for the working stress. Okay, and then of course the load in that case was, I think, the loading in that case was, I think, steady. Okay, now for this afternoon we will use again the ASME code, but this time the loading are suddenly applied. Okay, so what we have here is a rotating shaft. It carries a torque of 12,000 inch-pound, and then it is suddenly applied, and a bending moment of 8,000 psi, which is also suddenly applied, or applied suddenly. Applied suddenly. Okay, we are going to find a factor of safety given the yield point. This time the yield point is specified at 70,000 psi. Okay, so if you will recall, the formula of the ASME code is the working stress, which is 0.5, or the yield point in shear over factor of safety. Yield point in shear is 0.5, the yield point in tension, or factor of safety, is equals to 16 over pi d cubed, and then your constant Cm and Ct. This time, our Cm, our Ct should be appropriate for the load which is applied suddenly for torque, and also for moment applied suddenly. Okay, so let's go back to, I'm going to share the table for ASME table for constants, ASME constants. Okay, class, can you see now the table? Class, can you see?
Yes, sir.
The table, okay? So, for our case, it is not anymore a stationary shaft. It is now a rotating shaft. And then, the load is suddenly applied. Okay, so it could be this case or this case, no? But it did not mention, so the author, I think, specifies this case because he used Cm. It is a range from 1.5 to 2, so he uses Cm of 2 and Ct of 1.5. Okay, that is, so he used the suddenly applied load minor shocks, however, it is in the upper range. No? So, upper range of 2 for Cm and Ct 1.5. Okay, any question, class?
Wala na, sir.
Wala ra, okay ra. This is according to spots, no? In fact, wala man siya ni kuan. So, it is depending on the designer, whether he is going to use the 1.5 or the one here. Now Spatz chose the 2 and the 1.5. So let's go back. Okay, so our CM here is 2 and our CT is 1.5 from table 3-1. Okay, so we substitute values. This time, what we're going to use, it's not anymore 8,000 times 75% if there is a keyway, if you will recall, no? Because of stress concentration and because there is a reduction of the section of the shaft. We multiply it by 75%. Okay? However, what is given is that there is a yield point of 70,000 psi. So we are going to use the yield point. 0.5, 70,000 over the factor of safety, and then CM here is 2, and CT here is 1.5. And of course, you just solve that and try to take the factor of safety as the variable. The factor of safety as the variable, so you are going to compute it at 2.282832. Okay? Any question? So in this case, the difference between this and the first example was that this time, the yield point of the material is given. In the first case, there are no physical and chemical properties of the material. So, we use the 8,000 no? For commercial shafting, transmission shafting, according to the ASME code. Any question? Wala na question? No question?
Wala na, sir.
Okay. So let's go now to the second one. This time, we have a revolving shaft and it carries a bending moment of 27,000 inch-pound. Steady torque of 80,000. However, the torque fluctuates. No? The torque fluctuates 20% each way from the mean value. So the mean value is actually the steady torque. So your steady torque is 80,000 and then it fluctuates 20% of the 80,000. And the stress concentration factors are given to be 1.35. And the ultimate strength of the material is 120,000 psi. The yield strength is 90,000 psi. And the endurance limit of 44,000 psi. The shaft diameter is 3 3/8 inch. We are going to find the factor of safety using the first is by maximum shear stress theory, and later we will use the Macy-Hinkes theory. Okay? Now, let's first, if you will try to recall the formula for the maximum shear stress theory, you have average moment, and range moment, torque, average torque, and range torque. Okay? Now, for the torque, it is given that the steady torque is 80 and fluctuates at 20%. So which means your average is actually the 80 and then it fluctuates from 20% of that from top, no? So that is your range. The fluctuation is your range. So therefore, your average for the torque is 80,000 inch-pound. And then your range is 20% of that 80,000, which is 16,000 inch-pound. However, let's look at the moment. There is only one figure there, given that the revolving shaft carries a bending moment of inch-pound, 27 inch-pound. Now, that bending moment does not vary. Does not vary. So, if you use it in the formula, what should it be? The average or the range? Kay 27 raman na siya. Unless it is given as maximum of 27 and minimum of 15. So there is a variation of the moment. So you take the mean and you also take the range. However, there's only one. So there's only one bending moment, 27. So what is this figure? Huh? What is this figure? Is it for the average or the range moment? Why is it range? It does not fluctuate. 27,000. Huh? Or probably, this is supposed to be the average because any moment that is steady in value is average. Okay, if you try to recall, if this is your, so if these are your values of your maximum and your minimum, then of course the one in the middle is your average, and of course this one is that one is your range. Now that's all right for the torque, because in the torque it is specified that you have a steady torque of 80,000. Okay, so for the torque 80,000, and then it fluctuates 20% from that value. Okay, so we have 16,000. No, we have 16,000. We have 16,000 fluctuation from the steady of 80,000. However, for the moment, let us look at the moment. The value for the bending moment is 27,000 inch-pound, and it is only a single value. So meaning it did not fluctuate. So where is it supposed to be? Is it for the range or for the average? Is it supposed to be? Where should it supposed to be? Class, any idea? Any idea, class? The 27,000 bending moment of 27,000. Is it supposed to be on the average value or the range value, bending moment? Huh? Ada yan, unsa man ang kuan? Wala si Din. Okay, class, going back to the 27,000. Why is it range? We do not accept just because it is being written on the board that it is supposed to be range.
Tungod lagi sir kay bending moment siya sir.
Oh, so wala na tayo average yun. So always wala average, always range. If this one fluctuates, unsa naman na siya? If there is a fluctuation. In fact, like this one, for torque, you will notice the steady torque, which does not fluctuate, is 80,000. However, the fluctuation is given at 20. So, kining 80 mo na atong average. Ang 20% from that 80 will be the range. This one is the bending moment, which does not fluctuate. Unless, ingon nga, it goes up to another value and it goes down to another value. So what is supposed to be this 27,000? Is it for the average or for the range? It's supposed to be in the average. If you are going to follow the definition of average and range. Okay? Do you understand, class? Huh? Class, do you understand? So, your range is your fluctuation from your average. Your average is your steady. As what is given here. If these are your values of stress, moments or torque, then your maximum is here, your minimum is here. Then from that, you get your average in the middle, and this fluctuation are your range. So going back to the 27,000, is it supposed to be at the average or the range? According to our definition of average and range.
Average sir.
It's supposed to be average, okay? It is supposed to be average. That is average bending moment. Meaning the bending moment that the whole shaft experiences. So if this is your shaft, so probably you will have a moment here, bending moment, which is 27, and it does not change. This is inch-pound. That is for the shaft. However, we are examining here the element. And where is the position of the element? Let us say it is here. Will it always be there? Huh? Will it always be there? Class, will it always be there?
No, sir.
Why?
Revolve, no, sir.
Okay, so we have a revolving shaft. So therefore, at a certain position, it will be here, it will be here. So actually, this moment fluctuates on the element. Although it is a moment that is applied on the shaft steadily, but if you, on our analysis on the element experiences a fluctuating bending moment. So that is why it fluctuates. Now the bending moment here is opposite to the bending moment here. Is that the, what is, let us say that is the moment, bending moment. Or probably I would just simplify it something like this. So what is the stress on this? On this element?
Compression, sir.
Compressive. And then it reverses to
Tensile.
tensile. And then what are the magnitudes? The same in magnitude. So actually, in terms of the element, okay, it is range. It is from tensile to compressive, tensile to compressive. It is a range moment. So that is the reason. The reason why we put it as a range, not because it is written on the board. Any question? So this is actually moment range for the element. Any question? It depends because probably the moment also fluctuates. If this one will fluctuate, then you have an average. Because in this case, it is steady at 27,000. The question here is it always the case that when it is rotating, the average is always zero? Okay, in certain cases, if this will also fluctuate, then you do not have a zero average. Let us say it is from 27 at 1 maximum and then it goes to 12. Okay? Any question? Class, any question? But most cases, usually the moment does not, it is a steady application of the load. So that is why in most cases, the average is zero. Any question, class? Do you understand the explanation? Huh? Class?
Yes, sir. Kasabot, sir.
Okay na. So let's proceed. So we now have a asa na to? Average moment of 0 and the range moment of 27 because of the reason that it is a revolving shaft. And your element experiences this moment reversibly, no? reversing order from compressive to tensile. The effect of this on the bending moment is it is a alternating stress, alternating from compressive to tensile. So it belongs to the range moment. And then, of course, what is given are the stress concentration factors. For both cases, it is the same as for moment and torque, it is the same as K equals 1.35. Okay, so for bending and torsion, our stress concentration factor is 1.35. So we substitute it here to this equation. 0.5 and then 90,000 is your yield point in tension. Factor of safety 16 over pi d cube. Our diameter is 3 3/8 inch. And then of course, this time, this one is 0. So the value here is only the range part. Okay, this is only the range because our average is 0. However, in the torque, we have a average component and a range component. Okay, so simplifying what I did here, I first calculated this one, and it is this, no? And then solve for the factor of safety. So kining under the radical is this one. So you have to be quick in the calculator because this is a little bit complicated, no? Dagan kayo kuan. So the value of that square root quantity is this one. And then of course the factor of safety will be 1.988551. Any questions? Any question?
Very disappointed in your sister. Don't think I can tap this kind of all the stuff that stays. Hey, Twinkle.
Wala na? Okay, let's proceed with using the Mrs. Hincke's theory. So this time we are going to use the Mrs. Hincke. So we use the Mrs. Hincke's theory. So by the Mrs. Hincke's theory, we have the yield point over the factor of safety is equals to 32 over pi d cube. Again, similar to the maximum shear stress except for the 0.75. Okay? So we have already discussed this formula last time. So what we do here is just substitute values. 90,000 over factor of safety. Remember, this is yield point in tension. The difference between the maximum shear stress is that it is 0.5 over yield point over the factor of safety because this is yield point in shear. But for the Mrs. Hincke, and that is also the case for maximum stress theory, you have yield point in tension over the factor of safety, which is 32 over pi d cube, again, this quantity. And then we just substitute the same condition, the average torque and the range torque and the moments are all the same. So we still have the range moment because of the condition of the element that is being experienced by the element as your shaft is revolving. Okay. So what we have now here is we just substitute values. 1.35, okay. Remember the component which has the stress concentration factor is only the range component. Ang average component ani wala na siya ano? Average na siya. Ang naay stress concentration factor and range component. Okay, so substitute values, you have 90,000 pi d cube, and then again I calculated the one in the under the value inside the radical, and then extract the square root, which is this one. And so our factor of safety is 2.176601. Okay, class. So wala na question? So I think everything is clear. That will be all for today, no? Ora na siya, because the next meeting is another topic, no? This one is sample. At least we covered all examples for design of shaft using the ASME code, using the maximum shear stress theory and the Messier-Simkies theory. Okay, so you take your screenshot. You can also take a picture of kung ugma ganahan mo. Are you done with the first board class? Take a screenshot. Okay, so let's go to the next board. I will not erase the kwan. Okay ra na siya, no? The
share with your friend. This is me, Dokam Game. If you have any question, please comment below. I must share my screen.
okay na?
What is this? Okay, we literally saved the dog. This time we literally saved the dog. Maybe. Oh no, we can't save the dog.
Okay, any question regarding again, reminder, our exam will be on Wednesday next week, no?
Stay on my screen.
So because we still have time,
Okay, guys, let's go.
do you have anything to ask?
Okay, we can stuck in the circle.
Ito?
Okay, next round.
Oh, it's the same time, or probably I will adjust, no, depending. I think sayo ra kayo ang alauna. Huh? Again, the topics are
Okay na yan, sir.
Kanina lang, kailangan ko sandali.
Gano'n ka na may klase, sir.
Okay, wala na tayo. Unsa man class, do you think 1:30 is too 1 o'clock is too early? Ha? Basig maapikhan mo sa inyong panahon to. Okay, because we can adjust, probably we can have it at 1:30. Ugmas kwan. And of course, we will end at 3:30. Okay na ng 1 o'clock?
Okay na, sir. Kaya may klase po alas 3.
Oh, sige. Okay, go. What else? Do you have any specific? The coverage, again, balik-balik ra ko ani. Unsa man to una natong gikuan? Up to more circle, ha? Okay, the simple normal stresses are compressive and tensile. And then shearing. Simple shearing meaning only one. And the next is bending or flexural stress. What is important in that topic is that you should be able to determine the center of gravity when the cross-section is not regular or madili rectangle. If it is a composite figure, then you have to know where the center of gravity or the centroid of the cross-section, and then you also have to determine the moment of inertia, area moment of inertia. Those are the composite figures. Next is transfer superposition, or I think superposition, no? Superposition. Again, the same. For superposition, you have to, can you remember, if you have a certain, probably a certain, ano naman itong atong kuan example. And then we try to find a section here. What should be the stresses acting here? So it should be, if you cut, ano naman ito atong example? So if your load is there, and then you are going to find the stress at that section, you have to what? Transfer this here, and that one will become, these two will become moment in that direction. So more than siya. So you now have to. So instead of one, you now have two for superposition. So you have to evaluate. This one has to be on the centroid, location of the centroid of the cross-section. And then, of course, this one is a bending moment. It is distance from these two. And of course, that will be the same here. If we look at the section, it will also be this one.
Actually, one thing I forgot to say.
Because that is the reaction. Can you remember that class? Now, okay na? That is for superposition. And then, for transverse shear stress. Again, you have to know where the center of gravity or centroid of the cross-section. If it is composite figure, then you have to know about its centroid, about the center of gravity, and then you have to know the V bar A, where V bar is the distance from the centroid of the area. Remember, the area is an area between the outermost fiber to the location where you want to find the transverse shear stress. That is the area. It could be towards one direction or the other direction. It doesn't matter. You will get the same. However, V bar is the distance between the centroid of the area to the neutral axis. Okay? And it will be summation of V bar A if it is a composite area. Then of course the Mohr circle. Okay, class, wala na tayo kuan? Wala na tayo question?
Wala na dagay, sir.
Wala na. So, again, before we end our discussion, so you try to, I will still give you a chance. You look at the examples, no? There are examples, some examples in the PDF file that I have given you. I mean, problems, no? There are problems in the PDF file that I have given you. So you try to look at those.
Thank you, sir.
And probably you might have some questions. You only have another chance probably in Monday. Kung makuanta. So, as of now, it seems that wa pa mo katuon po kay wa man may question. Or probably nahurot na niyong tuon nga. Wa na may kapangutana.
Wala pa katuon, sir.
Wala pa di ay. So that is why I am giving 1 week, no? 1 week unta na siya. Okay, so can you turn on your cameras before we say goodbye? I will ask you to erase the board, ha? Dala. Turn on your cameras, please. Oh, okay na. Bantay, maigo ang kamera. Kaya rin ko na. Atong kuano mayo. Nandiyo mayo kay aron. Sa primero ni mong erase napa may puti-puti gon. Okay, class. So thank you for a successful class this afternoon, no?
Thank you, sir.
Thank you, bye.
Sir.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.
Bye.
Really? Yeah, really. You like going around people like this? You know what? That's fun. Don't touch my buddy. Oh, go ahead, bud. Do it. Do it.